So today we are going to start this support vector machine, right? As we have discussed yesterday.
Yes.
So this SVM is basically a classifier only. Like it is
Mhm.
used for classification problem only. Like if you have some data of different classes, we can use SVM in that. Okay.
Okay.
But it is totally a different kind of classifier. Like whatever we have studied, like KNN has a different concept. The tree-based classifier has different concepts, like this random forest decision tree, gradient boosting. Okay, logistic regression was again a kind of classifier only, which has different funda altogether. So similarly, support vector machine has also a different concept. We will see what it exactly it is. So initially, we will start with the definition, which you can see on the slide. SVM is a supervised machine learning model which finds an optimal hyperplane separating two class training data, such that the margin between the border points support vectors is maximum. Okay, so first of all, it's a supervised machine learning. It means whatever data you have, you should have the data features. I mean the data points having features plus the labels. So in supervised, you have labels of the data that these 100 are class A, these 100 are class B, these 100 are class C kind of thing. Okay. So that is like that is one thing. Second thing is it finds a optimal hyperplane. Okay, so in general, if I say don't get confused with the word hyperplane. It's like a plane. It's like it puts a plane between the data points of different classes. So basically, if you have some training data point, it will put a plane. So if it is a 1D data, it will put a say dot. If it is a 2D data, it will maybe put a line. If it is a 3D data, it will put a plane. If it is a 4D data, it will put a 3D plane. So that is why the name is hyperplane. Sometimes you have some data points which has 100 features. So then it will put a very high dimensional plane. That plane is a hypothetical, that is why it is called as hyperplane. So majorly what I mean to say that whatever your data is, it will try to put a hyperplane, it will try to learn a hyperplane. That hyperplane is not real, that is basically a hypothesis only, but it tries to learn a plane kind of thing between the two classes where it can separate out the data points. Okay, such that the margin between the border points is maximum. I will talk about this margin, border points, what is support vectors. These things will be clear once we move ahead. Um, just I wanted to know that you to know that okay, it is putting some plane over there. I will show you how it does. So this is like SVM features, not features exactly, but what SVM is actually. It's a binary classifier. It's a linear classifier. You can say, yeah. It puts a straight plane, straight kind of thing. It does not put any curve or something. It is a linear classifier. That is why it is called. And even on non-linear data, it works very well. In non-linear data, it will uh, what actually does in non-linear data, it will try to make it linear in some higher dimensional space. Okay. The statement which I am making, just try to understand. If you have some non-linear data, it will try to make it linear in some higher dimensional space. You just mark this statement. I will give you the example of this on the later slide. How you, if you have a non-linear data also, you can make it linear. Large margin classifier, I will come to that in next slide. Non-probabilistic, yes. So SVM majorly, anyway, like KNN or decision tree, random forest, none of them are probabilistic. Similarly, SVM is also not probabilistic. It just says that either class A or either class B. So you should understand what is a discrete classifier and what is a probabilistic classifier. Discrete classifier is where you have a hard code, output 0 or 1, class A or class B. That is discrete. And probabilistic is like you are telling the probability that 0.6% probability is that it is class A, 0.4% probability is that it is class B. So SVM is a discrete classifier. It will either say 0 or 1. Okay. Now discriminative classifier, yeah, that's the same thing. Discrete classifier basically. And supervised, we saw why supervised, because you need to know the labels beforehand. Okay, now I will talk about, like I said, that optimal hyperplane, margin, support vector, these things I will talk about. So now I am coming to that. What can you see here in the graph? You see 10 data points, right? 5 plus and 5 circles, isn't it?
Okay.
The plus ones are men, and the circle, this red circle ones are women. Okay, so you have 5 data points of men and 5 data points of women. And these are like weights versus sizes. These are weights versus sizes. So these are weights versus sizes. Okay, now you see, can you can see here 5 lines are separating these classes, these two classes, men and women. All
Yes,
these
for
5 lines are able to separate these classes, right? The gray one, the green one. But so what does SVM do? SVM finds the optimal line, the optimal plane, the optimal hyperplane in between this. Which one is the optimal? Which one actually SVM should choose? You know,
green.
actually, none of them is optimal. I will show you how optimal will look like. See, optimal
Okay.
will be this.
Hmm.
See, you have these data points, right? This, and this.
Hmm.
This. Now, all these
Hmm.
5 lines are able, this green line is also able to separate it, but it is not optimal. It is more
Okay.
biased towards the plus. I mean,
Okay.
if there is a, let's say, I will tell you, let's say there is a data here. This green line will say that this is a plus. Any data here, or say here, it will say that it is of plus category, but actually it is lying very, I mean, it could be this, woman also, right? But
Yes.
as this line is more near to women, it gives less space to the woman side and more space to the men side. So I'm just saying
Yes.
this, like, you know, a optimal plane would be this, exactly going between them. That's the optimal plane. Optimal plane will be as far as possible from the data points from each category. Okay. So from the data points of each category, so what is the nearest data point? This one and this one, and here this one and this one. So you choose the nearest data points on the boundaries, and you get that plane just in the middle. That's the optimal hyperplane. Now, how you get these optimal hyperplane and all this? It's a very complex mathematics behind that. You may not need to go in those details because that will again, I mean, take a huge lot of effort in understanding those Lagrange multipliers and all. I mean, it's a planar equation which then moves on. A lot of mathematical derivation was there. SVM I will tell you, SVM is one of the complex model, the most complex model in machine learning. If you go to the mathematical side, it took a huge amount of years to develop this model, and for binary classification, it is considered to be one of the strongest model. It is really superb. I mean, these days it was invented nearly. I mean, in after 2000 only, and it became very popular actually. But yeah, but then this neural network and all has come, so it has again become a conventional model only. But yeah, uh, till recently, it was one of the best model for classification. Still, it is used in a lot of industrial applications, maybe. Uh, but yeah, what I mean to say is, this is how it goes. That it basically puts a, now this is a 2D image, 2D data. That is why you are seeing a line. If it's a 3D, you will see a plane. So the idea is that this whole planar equation is there, which it finds, and how it finds? It finds with the help of these data points, the boundary data points. Okay, through the boundary data points, it tries to get this. Okay, through the
Yes.
boundary data points, it tries to learn this line, and or plane or whatever it is, and then it on any new data, it can say that you either fall this side or this side. So either on the positive distance or the negative distance. So that is the funda. Okay. Now let us see, delve into more of this. So this is now, how SVM does the classification. So, so what SVM will do? You have the data, right? You have the data of two classes. Say this is class A and this is class B. So what SVM will do? SVM will first find out those data points which are near to the other class, basically the boundary data points. So it finds the blue point, and it will draw a line going through that. So basically, you can say that this is the closest boundary for B, right?
Mm-hmm.
And you draw a line going passing through the boundary data points of red, and you can say that this is the closest boundary for A. Once you have established this, that these are the closest boundary, then you don't have to do, then you don't have to do much, but you have to place the plane in the middle. Okay. So, and what is the benefit? The benefit, this line, this plane is all hypothetical, okay? But it's like it is calculated so that from this plane now, I will tell you, from this plane now, which is calculated in the mid of both the boundaries, you see whether this is the test data is this side or this side. So if your data is lying here, it will be considered as of this class. If the data is lying here, it will be considered as of this class. It's like that. Okay. And another benefit of this is, instead of entire training data, only a support vectors are needed to determine the class of new test data. So like in KNN, if you remember, we need to calculate the minimum from all the data points, and then we used to take, say, k equal to 10. So we will be checking the 10 neighborhood, right? Nearest neighborhood and all. So all the
Yes.
points were taken into account there. Here the benefit, SVM is fast in testing. It's really fast while testing because you do not need to consider all this data. No, you just need this data, the boundary data, in order to find this plane and in order to make the decision whether the test data is on A or on A side or B side. So you just need these boundary data points. And you know what? These boundary data points
Mm-hmm.
are called support vectors.
Okay.
These boundary data points are only called as support vectors. So why are these called support vectors? Because they are supporting the classifier, they are supporting the model. Okay.
Okay. But it is always a straight line, or it could be a curved line.
No, no, yeah, it could be a curve also.
Mm-hmm.
It could be a curve also, but I will tell you this if it is a curve, if it is a non-linear boundary,
Mm-hmm.
support vector actually is a linear classifier. I mean, not a linear classifier in true sense, but what it does, if it is a curve, it will take it to a higher dimension. And in higher dimension, I will show you example. And in higher dimension, what will happen? It will become a linear straight line. So you can say that it will always be a straight line, yes. Maybe your data is not linear. Maybe your data has non-linearity and maybe a curve is required. But that curve, the SVM tackles in a very tricky way. It's called the kernel trick. What is it called? It is called kernel trick. So we'll
Yes.
see that in a moment that how that kernel trick works. Whenever you have this curvy kind of data, then also actually you can in the cases where you have curvy kind of data, there also SVM works fine with with retaining the linearity.
Okay. Okay.
You will see that.
Okay.
Okay. So that's the concept of maximum margin classifier, which we saw in the definition also. I told you that it will come. This is a very simple concept which we have discussed here already. The left hand side image you see is the optimal hyperplane, best margin, isn't it?
Yes.
It's the best margin. And on the right hand side, the line, that line is also straight. Okay, but it is not optimal margin. I mean, it is not the optimal hyperplane. It's not the maximum margin. It is a small margin, right?
Okay.
You see, the here this could be the maximum margin, right? Which you can get
Yes.
from both the classes. Maximum margin,
Mm-hmm.
isn't it?
Yes.
And here unnecessarily you have left this much of a space. Your line is here and you got margin here. See, what is margin? Margin is the equidistant from both classes. I mean, margin will be always be equal. I mean, it's not like here the margin is this much and here the margin is this much. So if you are giving margin only here this much, you will also consider the margin here this much only. So this is a very small margin and this is not considered right. This is not considered right. The the SVM makes sure that your margin is always maximum. SVM takes care of the fact that your margin should always be maximum. You fit this thing in your mind. Always SVM will draw the plane such that the margin is maximum. Now I will come to the examples where we have a trade-off that whether to keep margin maximum or to get the better accuracy. So I will come to that discussion also. But as of now, in the ideal condition, you just remember that SVM has maximum margin. Okay. Okay.
Okay.
Yeah. So now we are coming to that discussion. Can you see the two images on the right and left side? You see
Yeah.
the left hand side is called hard margin and the right hand side it is called soft margin. Now more interestingly, if you see the hard margin, does this hard margin have any error in classification? Is the line able to classify the data?
Hard margin.
Yeah, in hard margin, my
Yes.
question is, in hard margin, is the line able to classify the data points?
Yes.
Yes. But what about margin? Margin is
Very low.
good enough?
No.
No.
Margin is very low in hard margin.
Margin, where is the margin, man? If I draw the
Yeah.
boundary of this blue one and if I draw the boundary of this red one, where is the margin? Margin is almost zero, right? Isn't it? Here on the right hand side, if you see, the margin is good enough, right?
Mm. Yeah.
But is the plane able to classify the data point here? No.
Yeah. No.
This
No. One.
particular plane is not able to classify this one, right?
Mm.
This
Yeah.
is called misclassification. Misclassification. Now, which one is a better thing? Tell me. I mean, it's basically a trade-off kind of thing. It's a kind of a discussion. I mean, a debatable thing. Which one is
Mm.
better? This one is better or this one is better? Now, I will give you the counter arguments. If you say the hard margin is better, I will say, what if the data point is here, 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 or data points are here? No, if you go by hard margin, all these data points should belong to this class and all these data points should belong to blue class, isn't it? Because
Yes.
it is on this side of line. If you go by hard margin, all these test cases will fail. These data points are supposed to be in this class and these data points are supposed to be in this class. But because you have a line like this, these data points will be considered as red and these data points will be considered as blue, isn't it?
Mm.
Are you getting my point?
Yeah. Yeah.
If I say these two data points, just by looking you can say this one will be blue and this one will be red.
Mm.
As the margin you have chosen so hard that coming on this side will make it blue and coming on that side will make it red. So hard margin in this case, I mean, I was giving the counter argument that, well, on training data it's 100% accurate. On training data there is no misclassification, but when you will test you will find lot of data points which will be misclassified just because you have unnecessarily trained it very hard. Now, in soft margin, your training data may be 99% accurate only. Why? Because there is one misclassification. But your testing data will be very accurate. I mean, will be sufficiently accurate. Why? Because the problem of coming of data points here, here, still these data points will be blue only, and these data points will be red only. So the margin is good enough. So although on training data there is a misclassification, but on testing it will perform far superior than this. So I will go by soft margin. In this case only I am saying. So you can just read these points. If the points are linearly separated, but then margin becomes too narrow. It's not like that it's not separated. It is separated. It's linearly separated. Linearly separated means separated by a line, straight line. So the points here are linearly separated, but then the margin becomes very narrow. And in this case, soft margin, you see, the large margin solution is better even though one data points get misclassified. We have a trade-off between margin and the number of mistakes on training data. Okay, this is very important line. We have a trade-off between margin and number of mistakes on the training data. So you have to think whether I can afford misclassification on training data or not. So if there are 2-3 misclassification and but instead you are getting a good margin, go with that. Go with that for sure. That's soft margin. But if you have lot of misclassification because of margin, then maybe let's go ahead with the less margin only and try to classify more data. Training data should be accurately classified. So that's the kind of trade-off. So I hope you got the idea of margin and how this margin is related with the misclassification. Now
Yeah.
moving ahead in this, yeah. Now I am coming to the topic which you were asking earlier also, that if the data is itself non-linear, if the data is curvy kind of thing, then how does SVM takes care of that? Does SVM always put a linear boundary? Does SVM always put a straight line kind of thing? Or does SVM put a linear kind of boundary kind of thing? Or SVM does this curvy thing? So what I am saying, SVM will always draw a linear boundary, maybe in a
Mhm.
higher dimension, but it will put a linear boundary only. Okay. Now you see this 1D to 2D. You see the left, this example. Can you separate the blue one with the red one by making
Mm.
some boundary? See, if I make
No.
this boundary, then also there is huge misclassification here. If I make this as a boundary, sorry, if I make this as a boundary, this as a boundary, then also there is a huge misclassification here. So what to do?
Yes.
I cannot make a linear boundary here. I have to make some boundary like this, isn't it? I have to
Mm.
make boundary like this so that the outside world is red and the inside world is blue, isn't it?
Yes.
But kernel cannot make a curvy boundary. Kernel will always make linear boundary only. That is why it is
Mm.
called a linear classifier in some sense.
Okay.
This kind of data is called as linearly non-separable data. You cannot separate them by a linear boundary. Good enough?
Yeah.
Now, now see the solution. See the trick that kernel this SVM does. SVM does a very good trick here. That is called as kernel trick. What it does, okay, in our school days we used to study about this. If you remember, this is called as parabola. What is it called?
Parabola.
Parabola, right? And it
Yes.
has some equation. If I don't remember actually exactly, but it has some equation, y equal to x square minus 4ab, something like that, or 4bc, I suppose, something like that, where b and c are some kind of constant. X is the data point and y is the output function. Okay,
Yeah.
so this is the equation of a parabola. Now, what SVM does very trickily, you see what trick it uh, takes. It projects all these points on a parabola. Basically, from a straight line, one dimensional. See, this is 1D, right? So from a one dimensional, it makes it a two dimensional thing. And you will say, how does it make two dimensional? So nothing, just in place of x you put these data points in the equation. In this equation you just put the data points
Hmm. Yes.
and you will get the y's are this. Now
Parabola.
once you made project them on parabola, these 3 points will go on a lower side like this. Okay, and then seeing these 2 points as a boundary and seeing this single point as a boundary, you can draw a line which can linearly separate them. You see, very small margin is this much, but it is this line is able to separate the red and blue one linearly, isn't it?
Yeah.
Now again an example of 2D to 3D. In 2D the data points are lying like this, you see. Now if you are going to make a non-linear classifier, you need to make a curve like this in order to separate these data points. Because it's not like you can put a line which can separate the red and blue ones. No, it won't be possible. You have to put some curve like this, isn't it?
Yes. Yes.
What SVM does, it will again use some function. Like here it uses a parabola function. I know that this is a parabola, that is why I told parabola. Here I don't know what is the function, but let us suppose that there is a function phi. So you transform the points through this function phi such that this is a 2D space, such that in the 3D space it can get separated by a plane. You see, all the blue points are lying above the plane and all the red points are lying below the plane. And now the plane is linear, the plane is straight, isn't it?
Yes.
So this is basically a SVM trick, SVM kernel trick. This is called as kernel. This function here it's a parabolic function, right? Here it is
Hmm.
some phi function or something. These functions are also called as kernel. In machine learning SVM language, these functions which are used to project the lower dimension into higher dimension, this function itself is called as kernel. What it is called? Kernel.
Yeah.
So there are different kinds of kernel. Gaussian kernel, polynomial kernel, radial basis function kernel. So these are like now you will ask again a question. A very good question will come up in your mind. How do I know which kernel to use? How do I know, basically not like which kernel to use, how do I know that which function to use such that on a higher dimension it will get separated? It may happen that you choose a function and even on it taking a 2D to 3D or taking a 2D to 5D, you are not able to separate them out linearly with a straight plane. So that's the question. How do you come up with such kind of functions? So this is a very active area of research. You will find in research paper people give their own kernel, this kind of kernel we have used, that kind of kernel we have used. But in general, in practice, there are 3-4 kernels which are used, and in order to see which kernel will be effective, you just try all those 3-4 kernels, whatever works well, we chose that one. Okay.
Okay, okay.
So I told you there are three famous kernel. One is radial basis function. One is that polynomial kernel, and one is radial basis function. Polynomial, radial basis function, and Gaussian kernel. These are the three kernels which are very famous. And this is the example which I give. It will take the input values to some higher dimension. If you have set 10 features, so it will maybe take you to 20 feature or 15 feature, whatever it is, where it can get linearly separated. Good enough?
Yes, yes.
Okay. So yeah, this is again an important thing. We have talked about this a lot in linear regression also. Scaling,
Mm-hmm.
min-max scaling. So your data point, maybe you can just go back and watch the video of min-max scaling where I have told that whatever is the data, you have to bring it, I mean, you have to scale it between 0 to 1. So if you have data, I will tell you, if you will have data 2, 3, 4, 1, what will it become? Just subtract the minimum of this. So minimum is 1. So just subtract it, right? And then
Yeah.
divide them by max minus min. So max is 4, min is 1. So divided by 3. So this will become 0, this will become 1, this will become 0.66, and this will become 0.33. So this is maximum, this is minimum. See, this is minimum, this is maximum. But new features are this 0.33, 0.66, 10. This is the new feature. Why? It is a scale between 0 to 1. So in whenever you are going to apply SVM, just remember, just remember that scaling is very must. I remember I was doing a project for emotion detection in speech and I applied SVM. And I mean, all these days I have heard that SVM is very powerful classifier, this, that, these, those. And but I was not getting accuracy, and the accuracy which I was getting was so poor. I mean just 56%, 66% like that. And then I said that no, SVM is a bullshit. I mean, it doesn't work. People say that it works very well, but it doesn't work. And after lot of I mean after few days of this whole thing, I mean one fine night I just this thing came up to my mind that in SVM I think scaling is required, and I went to that the basic SVM and live SVM and documentation and all, and I found that if you do not do a scaling in SVM, it will, you will find a big blunder in the accuracies. And the next day I applied this min-max scaling, I applied SVM to the training as well as testing both the data. And from 66% the accuracy shooted to 82%. And that was like best thing. I mean, in 6 emotions, 82% accuracy we have achieved with this SVM. So whenever we talk of SVM, lot of people will not know about this, but this is very important. You must scale your data between 0 to 1 in order to apply SVM. Okay, because your features sometimes are totally on a different scales, and there SVM will find very difficult to put a linear boundary. So the data points has to be scaled in something. Okay. Okay, so this ends the SVM part. I will show you something. Can you see this image? Hello? Hello?
Me?
Hello?
Hello? Hello?
Yeah. Can you see this image?
Yeah, actually, yes, yes.
Okay. So you see, uh, this is the thing which I was telling na, in that I was doing some emotion detection kind of thing,
Mm-hmm.
and we have applied SVM there. So I have just transformed the features into 3 dimension in a 3D thing. So
Okay.
you can see this is the actual learned plane which SVM has learned. And on this side you will find the red points, and on this side you will find the blue points, isn't it?
Mm-hmm.
This is a SVM learned, a classification between happy and sad. In speech, a happy emotion and a sad emotion. On that, this is the classification on real data. And this is how SVM has learned the plane on real data. This is some Berlin database, IMUDB. So this is a guy, you see this again. A
It's three
plane has been
dimension.
learned, yeah,
Yeah, representation. Okay.
a plane has been learned, such that it will classify the happiness with sadness. I just wanted to show you that. This is a very, yeah, I mean, here the plane has not been able to learn very well, and the emotions were not, we were not able to classify the emotions, because this was not happy versus sad, it was anger versus happiness. So it's very difficult to for a machine to understand what is the difference between anger and happiness, because in both the emotions you will be talking loudly and
Yeah.
maybe aggressively. Yeah, so this is one thing. Just I wanted to show you some practical thing. That's why I showed you that graph. I mean that plot. But yeah, so this is how SVM, the whole thing about SVM is. So what you need to remember is majorly is it puts a optimal hyperplane. It is a large margin classifier. You have to choose whether to go for large margin or few misclassification you can handle, or you have to go strict. Even if you have small margin, it's fine if your training data classification is 100%. So which of these way we have to go? This is important concept. Then the kernel trick and scaling is very must. So these are the few things which you should keep in mind while applying SVM. Good enough?
Okay. Okay, yeah.
Okay, so